Welcome to Lecture 5. This week we changed topic. We're going to start talking about vector spaces and subspaces of vector spaces and linear independence of vectors. In Mathematics 2, we started talking about vectors in two-space or three-space. We talked about dot product, etc. Now it's time to generalize these concepts. A vector space is a non-empty set V on which two operations are defined. These operations are called addition and scalar multiplication, and they must satisfy the following 10 conditions. Condition number 1. If U and V are objects or vectors in our set V, then we must be able to add them together and still be in the set V. In other words, we need to be able to do vector plus vector is equal to a vector. And then addition of two vectors need to satisfy that U plus V is the same as V plus U. If we have three vectors, U, V, and W, it doesn't matter where we put the brackets, U plus V plus W must be the same as U plus V plus W. We need to have a zero vector, and by that I mean a vector which has the property that 0 plus U is equal to U and U plus 0 is equal to U for all vectors U. Rule number 5, for each U, we must have a minus U, and that will be an object which has the property that U plus minus U is equal to the zero vector. Let's move on to talking about scalar multiplication, or multiplication by a number. If K is a scalar, by which I mean a number, and if U is an object in the vector space, that would be the vector, then we need to be able to multiply the vector by the number and get something which is still in the set V. Rule 7, if K is a number, U and V are vectors, we need to be able to do K multiplied by U plus V is the same as KU plus KV. If K and M are numbers, we need to be able to do K plus M multiplied by U is KU plus MU. We need that K multiplied by MU is the same as KM multiplied by U. And finally, rule number 10, we need that the number 1 multiplied by the vector U is just the vector U. If all 10 conditions are satisfied, then we say that our set V is a vector space. Some remarks. If all the scalars that we're considering are real numbers, then we say that V is a real vector space. If instead we allowed some complex numbers K, then we would have a complex vector space. The objects in our vector space are called vectors, and these 10 conditions or these 10 rules are called axioms. It's possible to show that the zero vector is unique, and it's possible to show that the negative of U, that's the one we write as minus U, is unique for each U in V. The number 0 multiplied by the vector U must give us, or does always give us, the zero vector. Let me just pause here just to emphasize. The first 0 is a number, and the second 0 is the zero vector. minus u is always the same as the number -1 multiplied by u. And finally, if we know that ku is equal to the 0 vector, then we must have that either k is the number 0 or u is the 0 vector. If we want to show that a set with two operations is a vector space, we can follow these 4 steps. Step 1, identify the set V of objects, which we're going to call the vectors. Decide what our vector addition and what our scalar multiplication operations are going to be. It's perhaps a good idea to look at axioms 1 and 6 first. So in other words, check that adding 2 vectors together gives us a vector, and check that multiplying a vector by a number also gives us a vector. Axiom 1 is called closure under addition, and axiom 6 is called closure under scalar multiplication. But that's not enough. We also need to check the other 8 axioms, axioms 2, 3, 4, 5, 7, 8, 9, and 10. If all 10 axioms are satisfied, then our non-empty set V is a vector space. So first example, the vector space R to the power n for any n greater than or equal to 1 is a vector space. These are called Euclidean vector spaces. In Mathematics 2, we looked at R2 and we looked at R3. Next, let's look at the 0 vector space. Let V be a set containing only a single object, which we're going to call 0. And then we're going to define addition and scalar multiplication like this. 0 plus 0 is equal to 0, and k multiplied by 0 is equal to 0. I'm going to leave it for you to check that if the only object in our set is the 0 vector, and if addition and scalar multiplication are given with these formulae, then all 10 axioms are satisfied. Let's talk about the vector space of sequences. Let V be the set of all of the objects of this form: U1, U2, comma, dot, 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 comma, UN, dot, dot, dot. The key idea here is this is not a finite vector. This goes on all of the way to infinity, where U1, U2, U3, etc. is an infinite sequence of real numbers. We can say that 2 infinite sequences are equal if their corresponding components are equal, and we can define addition and multiplication like this. If we want to add 2 sequences together, we just take each component, say U1 and V1, and we add them together to be the new first component, and so on. Likewise, if we multiply a sequence by a number, all we're doing is we're multiplying each component in the sequence, or each term in the sequence, by that number. And then we're asked to show that this set V with these 2 operations is a vector space. We need to prove that all 10 axioms are satisfied. And I'm going to do them in order: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Axiom 1 was that if we have 2 objects or 2 vectors in V, then we can add them together and we're still in V. We know from Mathematics 2 that if we add 2 sequences together, we still have a sequence. So axiom 1 is satisfied. Axiom 2, U plus V is equal to V plus U. That's an easy one. That rule is true for numbers, and therefore straight away it passes on to being true for sequences. U plus, open bracket, V plus W, open bracket, is the same as open bracket, U plus V, close bracket, plus W. Just like axiom number 2, This rule is true for numbers, and that passes on automatically to sequences. Rule number 4, there is a zero vector such that 0 plus u is u and u plus 0 is u. We'll just take the sequence where all of the terms in the sequence are 0, and that will work. Axiom number 5, for each sequence we need to have a minus u. Well, that's straightforward. We'll just define minus u to be the sequence with minus u1, minus u2, minus 3, minus u4, etc. So axiom 5 is also satisfied. Axiom number 6, closure under scalar multiplication. Again, we know from mathematics 2 that if we take a sequence and if we multiply it by a number, then we get a sequence. So in other words, if k is a number, if u is a sequence, then ku is a sequence, so ku is in B. Axiom number 7, that's an easy one. It's true for numbers, so it's true for sequences. Axiom number 8, see what I wrote in number 7. Axiom number 9, again, see what I wrote in number 7. And that just leaves axiom number 10. We need to prove that the number 1 multiplied by our sequence u gives us the sequence u. Well, that's straightforward because 1u1 is just u1, 1u2 is just u2, 1u3 is u3, and so on. All 10 axioms are satisfied, so we have proved that V is a vector space. Let p to the power n be all of the polynomials of degree less than or equal to n. So in other words, it's the set containing all of the things like a0 plus a1t plus a2t squared plus dot 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 plus an t to the power n. Each one of the aj's is a real number, and n is either a natural number or n is 0. And we're going to let addition and scalar multiplication be defined in the obvious way. Polynomial plus polynomial, we'll just add them as functions. Polynomial multiplied by a number, again, we'll just multiply the function by the number. Show that Pn is a vector space. And before I go on, depending on which book you look in, there's different ways to write this. P to the power n, P subscript n, or just this ordinary P to the power n. As long as you see some sort of capital P and an n somewhere, it refers to this set. So to show that this is a vector space, we need to prove that all 10 axioms are satisfied. Let's do 1 and 6 first. If P is the polynomial a0 plus a1t, etc., and if Q is the polynomial b0 plus b1t plus, etc., can we add them together and still get a polynomial? Yes, P plus Q is still a polynomial of degree n or less. And what do we get if we multiply our polynomial by a number? Polynomial multiplied by a number is a polynomial, and it's still of degree less than or equal to n. So axioms 1 and 6 satisfied. That just leaves the other 8. Axioms 2, 3, 7, 8, 9, and 10 follow automatically from properties of the real numbers. So I'm not going to talk about those. I just want to look at axioms 4 and 5. Axiom number 4 was existence of a 0 vector. Axiom number 5 was existence of a minus u for each u. So what do we do for a 0 vector or a 0 polynomial? We'll just let our 0 vector or 0 polynomial be the 0 function. Does that work? Polynomial plus the 0 function, we still have the polynomial we started with. And for a minus vector, a negative vector, we'll just define minus b to be minus a0 minus a1t minus a2t squared, etc. Because then if we do p plus minus b, we'll just get 0, the 0 function, so the 0 vector. This proves that Pn is a vector space. Another example is the set containing all polynomials of degree exactly 2 with the same obvious addition of scalar multiplication. Is this a vector space? And the answer is no. Why? Well, think about the polynomials 1 plus x squared and 2 minus x squared. These are both polynomials of degree 2, so both of these polynomials are in V. But if we add them together, then we get the polynomial 3 plus x. That's a polynomial of degree 1. But V is the set of all polynomials of degree exactly equal to 2. So P plus Q is not in V. That means this set V is not closed under addition. It fails the first axiom, so this is not a vector space. An example from your textbook. Let V be the set of all real valued functions defined on a set D. We're going to add the functions in the obvious way. F plus G is just going to be f of t plus gt, and likewise multiplying by a number C, we'll do that in the obvious way. C multiplied by F is just going to be take the function and multiply it by a number. So, for example, if our domain is the whole real numbers, and if f is the function 1 plus sine 2t and g is the function 2 plus 0.5t, we can add them together to get 3 plus sine 2t plus 0.5t, or we could multiply g by the number 2 to get 4 plus t. A set of all functions of this type satisfy all 10 axioms, so that proves that this set V is a vector space. Another example, let R to the power 2 by 2 be the set containing all 2 by 2 matrices with real number entries. And we just mentioned there's different ways of writing the set. Some books use the notation capital M 2 2, so capital M for matrices and then subscript 2 2 for 2 by 2 matrix. I prefer the notation real numbers to the power 2 by 2 because it's similar to R2 or R3 or R4. We have 2 by 2 real numbers arranged in a grid. And then if we wanted to use a different set like C to the power 2 by 2 or Z to the power 2 by 2, then the notation is consistent. Let addition and scalar multiplication be the usual operations on matrices, just matrix plus matrix or matrix multiplied by a number. Show that R to the power 2 by 2 is a vector space. So we need to satisfy all 10 axioms. Let's talk about 1 and 6 first of all. These are both satisfied because matrix plus matrix is a matrix. In particular, 2 by 2 matrix plus 2 by 2 matrix is a 2 by 2 matrix. Axiom number 6, multiply a number by a 2 by 2 matrix, we get a 2 by 2 matrix. So they're satisfied. We have closure under addition and we have closure under scalar multiplication. Axiom number 2. U plus V, we know that if we're adding matrices together, it doesn't matter which order we add them in. So axiom number 2 is satisfied. Axioms 3, 7, 8, and 9, I'm going to leave for you to prove. I'm just going to prove 4, 5, and 10. So let's assume that you've proven 3, 7, 8, and 9. Axiom 4 was the existence of a zero vector. Here we'll just let 0 be the zero matrix, because then if we do the zero matrix plus any 2 by 2 matrix U, we just get U. Axiom number 5 was the existence of a minus U. That's straightforward. For U as before, we'll just define minus U to be the same matrix, but with minus in front of each entry. Because then if we do U plus minus U, we get the zero matrix, or the zero vector in this notation. And then finally, axiom number 10, what do we get if we multiply a matrix by the number 1? We just get the matrix that we started with. So assuming that you've proven the axioms, which I didn't, this proves that our 2 by 2, or M22, if you prefer that notation, is a vector space. Now, so far I've been using U plus V and KU for addition and scalar multiplication, but as we move to more complicated examples, it might be confusing. So instead, I want to introduce some new notation. This symbol is a plus inside a circle. I'm going to use this to denote vector addition. So just as we've been doing so far, vector plus vector, but now I'm going to be writing a plus in a circle. And for scalar multiplication, multiplying a vector by a number, I'm going to be doing this dot inside a circle. So for example, let V be the set R2, and I'm going to define vector addition and scalar multiplication as follows. For U plus V, I'm just going to do U1 plus V1, comma U2 plus V2. And for K multiplied by U, I'm going to do KU1, comma 0. So we have the usual addition here, but I have this weird scalar multiplication. So for example, if U is the vector 2, 4, and if V is the vector minus 3, 5, and if K is the number 7, U plus V is minus 1, 9, but K multiplied by U, 7 multiplied by 2 in the first position, and then just 0 in the second position, so 14, 0. The question is V, together with these two operations, a vector space? Well, I can tell you that axioms 1 to 9 are all true. Axioms 1 to 9 are all satisfied, but I'm going to leave that for you to check. I want to talk only about axiom number 10. And axiom number 10 fails. Axiom number 10 is not true. And for example, it fails if U is the vector 0, 1, because then 1 multiplied by U, 1 multiplied by the vector 0, 1. In the first coordinate, we do the scalar 1 multiplied by the first component of U, so 1 multiplied by U. And in the second component, we just put 0. So that's just 0, 0, which is not U. So axioms 1 to 9 are true, but axiom 10 is false. Therefore, this set V is not a vector space with these operations. Next example. let V be the set of strictly positive real numbers. So in other words, V is the open interval from 0 to infinity. Let U and V be any vectors in V. So in other words, we're going to take any real numbers which are strictly greater than 0, and then we're going to let K be a scalar. We're going to define vector addition and scalar multiplication using these rules. U plus V is going to be the number U multiplied by the number V. K multiplied by the vector. Oh, there's a typo here. This should be a U. K multiplied by the vector U is going to be the number U to the power K. So what do we have? So we have weird addition, and here we have weird scalar multiplication. So let's just try with some numbers. For example, 1 plus 2. The way we add two numbers together is we just multiply them. So it's going to be 2. And the number 2 multiplied by the vector 1 is 1 to the power 2, which is 1. So that's weird, right? 1 plus 2 is 2. 2 multiplied by 1 is 1. Show that V is a vector space with these operations. I'm going to prove axioms 4, 5, and 7. I'm going to leave the other ones for you to prove. Axiom 4, existence of a zero vector. The zero vector in this space is the number 1. In other words, the zero vector is equal to the number 1. Why? Because if we do a vector U plus the vector 0, that's the same as the number U multiplied by 1, which is U. And that's what we want. Axiom number 5, the negative of the vector U is 1 divided by the number U. Why? Because when we add them together, U plus minus U, that's the same as multiplying the numbers. U multiplied by 1 over U, which is equal to the number 1. But remember, the number 1 is the same as the 0 vector. Axiom number 7. The number K multiplied by the vector U plus the vector V. Okay, vector U plus vector V is the number U multiplied by number V. And then if we multiply it by the number K, that's the same as our numbers to the power K, or U to the power K, V to the power K. But that's then just K multiplied by the vector U plus K multiplied by the vector V. So axiom 7 is satisfied as well. As long as we can assume that you've proved the other axioms are true, this proves that V is a vector space with these operations. Next, let's talk about subspaces. A subset W of a vector space V is called a subspace of V if and only if W is itself a vector space under the same vector addition and scalar multiplication operations that we used on V. The definition of a vector space has these 10 conditions or 10 axioms. However, if a particular 2 of these 10 axioms are satisfied, then the other 8 are automatically passed on from V to W. So that means that if we want to decide if W is a subspace of V, then in practice we only need to check 2 things. And I can show that in this theorem. Suppose that V is a vector space and suppose that W is a subspace of V. Then W is a subspace of V if and only if axioms 1 and 6 are satisfied. So to say that another way, we just need to check that our subset W is closed under vector addition, scalar multiplication, and then we get the other 8 axioms free of charge, and we've shown that it's a subspace. We only need to check axioms 1 and 6. For example, if V is any vector space, and if W is the set containing only the 0 vector, then W is closed under scalar multiplication and addition because 0 vector plus 0 vector is 0 vector, and K multiplied by 0 vector is equal to 0 vector. And that's it. That's all we need to check. That proves that W is itself a vector space, so therefore W is a subspace of V. Next, let's V be the vector space R3 or R2 if you wish, with the usual addition and scalar multiplication. If W is a line through the origin, then if we add 2 vectors on that line, or if we multiply a vector on that line by a number, then we're going to get another vector on that line. Let me say again, look at the left picture. If U and V are 2 vectors on the same line, add them together, we're still on the same line. Or if we take a vector U on this line and we multiply it by a number, then we're still on this line. So W is closed addition, scalar multiplication, so W is a subspace of R3, or R2 if you wish. Now let V be the vector space of all functions defined on the real numbers. And let P, no numbers, just P, be the set of all polynomials. That V is a vector space. I've written here left for you to prove, but I think we've already talked about that. Because if we do polynomial plus polynomial, we get a polynomial. And because if we do scalar multiplied by polynomial, we get a polynomial. That means that P is closed under both addition and scalar multiplication. So therefore, P is a subspace of V. Also, P to the power n, that's the vector space of all polynomials of degree n or less. This is a subspace of P. I leave that for you to prove. Now let's talk about a subset of R2 that is not a subspace. Let W be all of the points in the first quadrant. In other words, be all of the points where x is greater than or equal to 0 and y is greater than or equal to 0. This set is not a subspace of R2 because it's not closed under scalar multiplication. For example, if we take the vector 1, 1, and if we multiply it by the number -1, then we get the vector -1, -1. But -1, -1 is not in W. We can't do vector multiplied by a number and still be in W, so W is not a subspace. Now remember what symmetric matrix means, and also remember that we can do symmetric matrix plus symmetric matrix, and we still have a symmetric matrix. And if we do a number multiplied by a symmetric matrix, then we have a symmetric matrix. This proves that the set of all n by n matrices, all symmetric n by n matrices, is a subspace of the vector space of all n by n matrices. For the same reason, the set of all upper triangular matrices is a subspace of the set of all matrices of that size. The set of all lower triangular matrices is a subspace of the vector space of all matrices of that size, and the subset of all diagonal matrices is a subspace of the set of all matrices of that size. Now I want to give a subset of R n by n where it is not a subspace. The set W of all invertible matrices is not a subspace of R n by n. Why? Because invertible matrix plus invertible matrix is not always invertible. For example, if U is the matrix 1, 2, 2, 5, and if V is the matrix -1, 2, -2, 5, both of these matrices are invertible. I leave that for you to check. But U plus V is not invertible. And I've written why. I want you to think about why we know straight away that U plus V is not an invertible matrix. You can ask me at the end if it's unclear to you. That means that W is not closed under addition. We have invertible matrix plus invertible matrix is not invertible. Invertible matrix plus invertible matrix is not in W, so W is not closed under addition. Therefore, W is not a subspace of Rn by n. A line in R2 that does not pass through the origin is not a subspace of R2 because it does not contain the zero vector. One of the axioms was that there must exist a zero vector. Anytime I give a vector space like here, and I don't explicitly say what vector addition and scalar multiplication mean, then you should assume that it's just the obvious ones. Theorem: if W1 and W2 are both subspaces of vector space, then their intersection is also a subspace of V. Let's prove this. First, note that the zero vector is in W1 intersection W2 because the zero vector is in W1 and the zero vector is in W2. So that proves that W1 intersection W2 is not empty. So we need to prove two things. We need to prove that W1 intersection W2 is closed under vector addition and that it's closed under scalar multiplication. For vector addition, remember we know that both W1 and W2 are closed under vector addition because they're subspaces. If U and V are vectors in W1 intersection W2, then they're both vectors in W1, so we can add them together and we know we're still in W1. Likewise, if U and V are vectors in W1 intersection W2, then that means U and V must be in W2. Because W2 is closed under vector addition, we can add them together and we're still in W2. But that then implies that U plus V is in W1 plus, intersection W2. Another typo which I shall fix later. And for scalar multiplication, similar argument, because W1 and W2 are closed under scalar multiplication. If U is a vector in W1 intersection W2, that implies U is in W1, which implies KU is in W1, and the same for W2. If U is in the intersection of W1 and W2, then U is in W2, which implies KU is in W2. So therefore, another typo, KU must be in W1 intersection W2. This proves that W1 intersection W2 is closed under vector addition and closed under scalar multiplication, so therefore it is a subspace. Now, it doesn't have to just be two subspaces. We could have any finite number of subspaces of a vector space V, take the intersection, and we also have a subspace of V. So, for example, let's suppose we're considering the vector space R3 with the usual addition and scalar multiplication rules. And let's suppose that W1 and W2 are planes passing through the origin. That means they are both subspaces of R3, so their intersection must also be a subspace of R3. And their subspace, so their intersection, assuming they're different planes, is just going to be a line passing through the origin. Let's talk about linear combinations. Let's suppose V1, V2, V3 up to Vr are vectors in a vector space V, and then we're considering K1, V1 plus K2, V2 plus dot 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 plus Kr, Vr. That's number vector plus number vector plus dot 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 plus number vector. This is called a linear combination of the vectors V1, V2 up to Vr, and the scalars here are called coefficients of the linear combination. Theorem. Let's suppose S is the set containing R vectors. Let's suppose this is a non-empty set of vectors in a vector space V. Then the set of all possible linear combinations of vectors in S. So that's the set containing everything which looks like C1 W1 plus C2 W2 plus dot 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 plus CR WR for numbers Cj. This is a subspace of V. And in fact, we can go further. This is the smallest subspace of V that contains all of the vectors in S. And by smallest here, I mean that any other subspace which also contains S must also contain W. Let's prove this. For part one, we need to prove closure under vector addition, and we need to prove closure under scalar multiplication. So let's take two objects in W. So let U be this linear combination of W1 up to WR, and let V be this linear combination of W1 up to WR. And let K be any scalar, any number. If we do U plus V, we're going to get A1 plus B1 W1 plus A2 plus B2 W2, etc. That's a linear combination of the vectors W1 up to WR. And if we do KU, then we're going to get KA1 W1 plus KA2 W2 plus etc. And that's also a linear combination of W1 up to WR. So we're having linear combination plus linear combination is a linear combination, and number multiplied by linear combination is a linear combination. This proves that W is closed under addition and closed under scalar multiplication. So this proves that W is a subspace of V. And for part two, we need to prove that W is the smallest such subspace. So let's let W tilde be another subspace of V that also contains all of the vectors in S. Because W tilde is a subspace, that means it's closed under vector addition, scalar multiplication. So that must also contain all of the linear combinations of W1 up to WR. But that means that W is a subset of W tilde. And then we're finished. That's what we needed to prove. This subspace is an important subspace that we're going to be talking about throughout the term. If S is a non-empty set of vectors in a vector space, then span S is the subspace containing all possible linear combinations of the vectors in S. This is called the subspace spanned by S, or if you wish, just span S. And we're going to talk about this a lot this term. We're going to take a 10-minute break now, and then I'm going to continue talking about span S, or the subspace spanned by S. And now let's continue. The standard unit vectors in Rn are 1, 0, 0, 0, 0, 0, 1, 0, 0, etc. These vectors span R to the power n because every vector v can be written in this way as a linear combination of E1 up to En. So in other words, Rn is equal to the span of the vectors E1, E2 up to En. Let's suppose we consider the vector space R3 with the usual additions, usual scalar multiplication, and let's let U be any non-zero vector in R3. Then the span of U, in other words, the set of all scalar multiples of U, is going to be a line through the origin, the line containing the vector U. If we have two non-zero vectors in R3, then the span of U and V, that's the set of all linear combinations of U and V, is going to be the plane which contains U and contains V. This is a plane through the origin, with the proviso that if U and V are parallel, then we would get a line instead of a plane. Let H be the set of all vectors of the form A minus 3B, B minus A, B. So in other words, H is the set containing all of the vectors A minus 3B, comma B minus A, comma A, comma B, such that A and B are real numbers. This is a subset of R4. Show that as well as being a subset, is also a subspace of R4 with the usual addition, usual scalar multiplication. Now, if we write this vector as a column vector, we can see we can write this vector as A multiplied by 1 minus 1, 1, 0, plus B multiplied by the vector minus 3, 1, 0, 1. So in other words, H is the span of two non-zero vectors. Because a span of some vectors is always a subspace, therefore H must be a subspace of R4. The polynomials 1, x squared, xn span the vector space Pn. That's the vector space of all polynomials of degree n or less. Why? Because every polynomial in Pn can be written as a linear combination of 1, x squared, etc. We can write this as Pn is equal to the span of the vectors 1, x squared, etc. Next example, for what value of h will the vector y be in the span of the vectors v1, v2, and v3 if v1 is the vector 1 minus 1 minus 2, v2 is the vector 5 minus 1 minus 7, v3 is the vector minus 3, 1, 0, and y is the vector minus 4, 3, h. Let me say again, for which value of h will y be in the span of v1, v2, and v3? Well, y is in the span of these vectors if there exist scalars c1, c2, and c3 such that y is a linear combination of v1, v2, and v3. In other words, such that y is equal to c1, v1 plus c2, v2 plus c3, v3. So in other words, for y to be in the span of these vectors, we want there to exist numbers c1, c2, and c3 such that this equation is true. Another way of saying that is we want this linear system to be consistent. Y is in the span of V1, V2, V3 if and only if this linear system is consistent. If we write down the augmented matrix for this linear system, and then if we check page 51 of your textbook, this is row equivalent to this new augmented matrix, this row reduced augmented matrix. And then we can see that the linear system is consistent if and only if H is equal to 5. If H is not 5, then we have a pivot in the right-hand column, and that tells us that the linear system is inconsistent. So the answer to this question is Y is in the span of V1, V2, and V3 if and only if H is equal to 5. In general, if we want to learn if a vector y is in the span of some vectors v1, v2 up to vr, then we start by writing the augmented matrix, first column v1, second column v2, and so on, final column y, and then we row reduce this to see if our linear system is consistent or inconsistent. So for example, consider the vectors u is 1, 2, minus 1, and v is 6, 4, 2. Show that y is a linear combination of u and v. In other words, show that y is in the span of u and v. Show that x is not a linear combination of u and v. In other words, show that x is not in the span of u and v. Now, because we're doing two things at the same time, I'm going to start with an augmented matrix with all of the information in. First column u, second column v, third column y, fourth column x. And then I want to row reduce this, and I'm leaving it for you to check. Please check that if you row reduce this matrix, we get this new matrix. Now, to answer the first question, let's cross out the red column. We'll forget that's not there. Just look at the, we'll pretend that's not there. Just look at the green and the orange part. We can see that if we just look at it green and orange, then the linear system is consistent. That means that y is a linear combination of u and v. And in fact, we can read off that y is minus 3u plus 2v. But if we cross out the orange column, if we forget that, if we pretend that the orange column is not there, we just look at the green and the red, now we have a pivot in the right-hand columns, and now we have an inconsistent linear system. That means that y is in the span of u and v, but x is not in the span of u and v. Do the vectors v1, v2, and v3 given here span R3? We need to answer the question if y is any vector in R3, can we find scalars or numbers k1, k2, and k3 such that y is k1, v1 plus k2, v2 plus k3, v3? That is the same as the question, is this linear system consistent for all y? There's first column v1, second column v2, third column v3, multiplied by the column vector k1, k2, k3 is equal to the column vector y1, y2. Is this consistent for all y? Or an equivalent question, Is the following matrix invertible? The answer to all of these questions are either yes or no. And in fact, the answer is no. Why? Because the determinant of this matrix is equal to 0. I'll leave that for you to check. That tells us that our vectors v1, v2, v3 do not span R3. Let's talk briefly about solution spaces of homogeneous linear systems. Let me remind you that homogeneous means that the numbers on the right of the equal sign in our linear system are all equal to 0. Theorem: the solution set of a homogeneous linear system AX equal to 0 of M equations in n unknowns is a subspace of Rn. Let's move on to our next idea. I want to explain that solution sets, that spanning sets are not unique. For example, note that the span of the vectors 1, 0, and 0, 1 is R2. And that is also the span of the vectors 1, minus 1, and 1, 1. Why? Because if we do 1, 0, minus 0, 1, we get 1, minus 1, and 1, 0, plus 0, 1 is 1, 1. So that means these two vectors on the right are linear combinations of the vectors on the left. And likewise, the vector 1, 0 is a half 1 minus 1 plus a half 1, 1, and the vector 0, 1 is a minus a half 1 minus 1 plus a half 1, 1. So that means the vectors on the left are also linear combinations of the vectors on the right. In general, let's suppose that V is a vector space. Let's suppose S and T are non-empty sets of vectors in V. Then we can have that the span of S is equal to the span of T if and only if every vector in S is a linear combination of those in T, and each vector in T is a linear combination of those in S. Our final topic for today's lesson is the topic of linear independence. In R2, every vector can be written as a linear combination of I and j in exactly one way. For example, this vector is the vector 3i plus 2j. There's no other way to write this vector using I and j. But what if instead of two vectors, we have three vectors? Let's suppose we have I, j, and w. And then the same blue vector as before. How can we write the vector 3, 2 in terms of I, j, and w? Well, I could do 3, 2 is 3i plus 2j plus 0w. I could do 3, 2 is 3i plus j plus root 2w, or I could do 3, 2 is 4i plus 3j minus root 2w, or ... In fact, there's infinitely many ways to write 3, 2 in terms of I, j, and w. Why is this happening? This is happening because each of these three vectors can be written as a linear combination of the other two. For example, w is root 2i plus root 2j, or I is 1 over root 2w minus j, or j is 1 over root 2w minus I. What that means is 2 is the correct number of vectors in R2. If we have 2 vectors, like I and j, then we could write any other vectors as a linear combination of them in a unique way. But 3 is too many vectors to do this. Let's formalize these ideas. If S is a set of 2 or more vectors in a vector space V, then S is said to be a linearly independent set if no vector in S can be expressed as a linear combination of the others. And a set which is not linearly independent is said to be linearly dependent. Theorem: a non-empty set S in a vector space V is linearly independent if and only if the only coefficients k1 up to kr satisfying this vector equation are k1 is 0, k2 is 0, up to kr is 0. In other words, they're linearly independent if the only solution of this equation is that all of the kj's must be 0. For example, I, j, and k form a linearly independent set in R3. So by the theorem, we need to prove that if we start with the equation 0 is equal to k1i plus k2j plus k3k, then we must have that k1, k2, and k3 are all 0. But this equation is just the same as writing the vector 0, 0, 0 is equal to the vector k1, k2, k3, and that implies that k1 up to k3 must all be 0. So therefore, S is a linearly independent set. Equivalently, we can say that the vectors I, j, and k are linearly independent vectors. Next example, are the vectors v1, v2, and v3 linearly independent or linearly dependent in R3? That's the same question as saying, are there non-trivial solutions to k1, v1 plus k2, v2 plus k3, v3 equal to 0? Or are there non-trivial solutions to this? Or in terms of a linear system, are there non-trivial solutions to this linear system? I'm going to answer this in 2 different ways. What we could do is we could solve this linear system. For example, write down the augmented matrix, row reduce it until we get to row reduced echelon form, and then read off. And if you did that, you would find that the solution is k1 is minus a half k3, k2 is minus a half k3, and k3 is a free variable. That means that there are non-trivial solutions, so therefore v1, v2, and v3 are linearly dependent vectors. Another way to answer this question is to calculate the determinant of this matrix. Let A be the matrix where the first column is v1, the second column is v2, and the third column is v3. And then calculate the determinant of this matrix. And I leave it for you to check that the determinant of this matrix is equal to 0. That means A is not invertible, and that then implies that AKE 0 has infinitely many solutions. Because there are non-trivial solutions, that implies that our 3 vectors are linearly dependent vectors. An example from a textbook. Determine whether these 3 vectors are linearly dependent or linearly independent in R4. To answer this, we start with the same equation. We start with k1 v1 plus k2 v2 plus k3 v3 is equal to 0 vector. And we need to answer, do there exist non-trivial solutions? Now, I'm going to leave the details for you to check, but for this example, we find that the only solution of this is the trivial solution. K1 is 0, K2 is 0, K3 is 0. From that, we conclude that these three vectors are linearly independent. I'm going to move on. You can come back and read this example at a later time. Show that the polynomials 1, x squared, comma, dot, 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 comma, x to the power n form a linearly independent set in Pn. Well, let's name these. Let's call the first one P0, the second one P1, the third one P2, etc. We need to show that the only solution to A0 P0 plus A1 P1 plus dot 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 plus AN Pn equal to 0 is the trivial solution. And that's the same as the equation A0 plus A1x plus A2x squared plus dot 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 plus AN xn is equal to 0 for all x in the real numbers. Now recall that a non-zero polynomial of degree n has at most n roots. If these aj's are not all 0, then we would have a non-zero polynomial with infinitely many roots, and that's not possible. So that tells us that we must have aj equal to 0 for all j, and therefore 1x, x squared up to xn are linearly independent. Another example from the textbook. Determine whether these polynomials are linearly dependent or linearly independent in P2. P subscript 2, I would write this as bold or double bolded P to the power 2. And again, we need to start with the equation K1 P1 plus K2 P2 plus K3 P3 equal to 0. And then we need to say how many solutions are to this equation. Is it only the trivial solution, or are there other solutions? And as it says at the bottom, for this one, it turns out there are non-trivial solutions. So therefore, P1, P2, P3 are linearly dependent. I'm going to move on again. You can come back and read this later. Theorem, a finite set that contains the 0 vector is linearly dependent. As long as if one of the vectors in our set is 0, then it's linearly dependent. A set with exactly one vector is linearly independent as long as that vector is not 0. And a set of exactly two vectors is linearly independent if and only if neither vector is a scalar multiple of the other. So for example, let's talk about the linear independence of two functions. And the functions we're going to take are f1 is equal to x and function 2 equal to sine x. These are linearly independent vectors in f. That's the vector space of all functions defined on the whole real line, because neither function is a scalar multiple of the other. But on the other hand, sine 2x and sine x cos x are linearly dependent because, we remember, sine 2x is 2 sine x cos x, so that means g1 and g2 are scalar multiples of each other. We can think if we think in R3, we can think geometrically. If V1 and V2 are in the same line, pointing in the same direction, that means they're scalar multiples of each other, so they're linearly dependent. If they're on the same line but pointing in opposite directions, again, one vector is a number multiplied by the other one, so linearly dependent. If they're not on the same line, if they're pointing in different directions, then they're linearly independent. And we have a similar idea if we have three vectors in R3. If they're all in the same plane, then they're linearly dependent. One vector is a linear combination of the other two. But if they're pointing in different directions, for example, if V1 is not in the plane which contains V2 and V3, then they're linearly independent. Let S be a set of R vectors in Rn. If R is strictly greater than n, then we know that S is linearly dependent. I'll leave that for you to think about why that's true. And I'm going to finish by talking about linear independence of functions. Are the functions sine squared x, cos squared x, and 5 linearly independent or linearly dependent? Well, they are linearly dependent. Why? Because if I calculated 5f1 plus 5f2 minus f3, 5 sine squared plus 5 cos squared minus 5, of course that's just equal to 0, because as everybody remembers from high school, sine squared plus cos squared is equal to 1. Now this one was easy, but for more difficult ones, we need something called the Wronskian. If we have n functions which are n minus 1 times differentiable, then we can write down the determinant of this matrix. Now, first column is the first function, and then the derivative of the first function, the second derivative of the function, all the way down to the n minus 1 derivative. Because this is an n by n matrix, so start with 0 derivatives at the top and finish with n minus 1 derivatives. And then the second column, we do the same thing, but for f2. Third column, same thing, but for f3, and so on. The determinant of this matrix is called the Wronskian of the functions f1 up to fn. And that's useful because of this theorem. If these functions have n minus 1 continuous derivatives, and if the Wronskian of these functions is not always equal to 0, then these functions are linearly independent in the set of all n minus 1 continuously differentiable functions. So basically this says, calculate the Wronskian and see if the Wronskian is always equal to 0. If it's always equal to 0, they are linearly dependent. If the Wronskian is not always equal to 0, then they are linearly independent. So for example, use the Wronskian to show that x and sine x are linearly independent vectors. What we do is we calculate the Wronskian. The first column is x, and then the derivative of x, which is 1. And the second column is sine x, and then the derivative of sine x, which is cos x. We calculate this determinant, x cos x minus sine x, and then we can see that this is not always equal to 0. For example, w at pi over 2 is not equal to 0. That tells us that these two functions are linearly independent. One more example. Use the Wronskian to show that 1, e to the power x, and e to the power 2x are linearly independent vectors. So we calculate the Wronskian. We have three functions, so it's going to be the determinant of a 3 by 3 matrix. For the first column, we have 1, and then the derivative of 1, which is 0, and then the second derivative of 1, which is also 0. And then we move on to the second function, e to the power x. Differentiate e to the power x, we get e to the power x. Differentiate it the second time, we still have e to the power x, and so on. The Wronskian the determinant of this 3 by 3 matrix is 2e to the power 3x, and this is not equal to 0 anywhere. So that tells us that f1, f2, and f3 are linearly independent. We're going to need the Wronskian when we study differential equations next semester in Mathematics 4. So remember this idea, we're going to need this next semester. And that's all I have for this week. Are there any questions?